Okay, so as we saw, that Pons Asinorum version of the proof of the isosceles triangle, or the base angles theorem as we're calling it, a little bit complex, just a little bit complex, but it didn't need to be that complex as we're about to see. So it still needs some more information. So here I have the same kind of picture. I've got myself AC being congruent to AB. We're trying to prove that the two base angles B and C are congruent to each other, but you're going to see that this proof far easier. All we have to do is add a single segment to this picture. And the segment that we're going to join in here is we're going to find the midpoint of the base there, this BC. And can I find that? If I was going to use my compass and straight edge, what I would use is just the two-tailed fish construction. I could easily find that point M, and then connect point M to point A in order to make my two triangles. Now this particular segment has a special name. It's called a median. Like the median of a highway goes right down the middle of the highway. I'm going to write down sort of a definition here of a median. Actually, I need to write this over here on Notability. Okay, so a median is a segment that says segment if you couldn't read it. Oh, here, let me clean that up for you. That connects the vertex of a triangle. I should say a vertex of a triangle. Not to be confused, it doesn't have to go from the vertex angle. This one is gonna, for the purposes of this proof, it needs to. A vertex of a triangle to the midpoint of the opposite side. Make sure you write something down here for this new vocabulary word median. We're drawing in a segment going from a vertex midpoint of the opposite side. All right, so since I have drawn this in there and I can easily construct, I can find this point M, this midpoint, every segment would have a midpoint, and it would make the CM congruent to MB. I would also have, by the reflexive property, in case you needed that again, the definition of a median, what was I saying? Reflexive property. The median would be congruent to itself. And so these two triangles are congruent by side, side, side. And once the triangles are congruent by side, 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 then we conclude that our two base angles are congruent by CPCT. Ooh, misspelled it. There we go, CPCTC. Well, that's it. That's all we needed. We could, hey, that's just like, I see that bridge over there, that bridge that everybody's like, I'm not sure if they're falling off, if they're just jumping off. This whole Pons Asinorum, I just bypassed the whole entire thing. It's like I don't know, I used a rocket to get across this chasm, whatever it is. Like going back to that original picture, that etching, I don't even know what that bridge was even supposed to cross. Yeah, so let's take a look at another version of this same proof. Also very, very easy. We're just going to add an extra segment to it. And this segment is going to be called a median. Not a median, we just did median. It's an altitude. So to make an altitude, you start at a vertex, and then you have to make a right angle with the opposite side here. Now, this altitude, as it's going to be called here, altitude, sometimes it's in the triangle and sometimes it's not in the triangle. It depends on what type of triangle that we have. So, for example, let me come back over here to a notepad. And if I had myself an obtuse triangle, and I were going to draw in an altitude, and this altitude was going to go from this vertex here to this opposite side right there. You can see that I can't draw it on the inside. It wouldn't make a right angle. So what I do have to do is I have to extend out that side of the triangle before I can bring down my altitude to make a right angle. And you've probably seen this. Altitudes are associated with the height of the triangle. Why did I just do that? I don't know. All right. It's associated with the height of the triangle. And the height and the base always have to make a right angle, right? We've seen this in terms of finding the area of a triangle here. So I'm going to write down a definition for an altitude. So an altitude is a segment that is going to join the vertex or a vertex of a triangle, and it's going to be perpendicular to either the opposite side or a line containing the opposite side. Let me write something down here. So an altitude is, let's underline that. Really highlight it so it pops out. An altitude is a perpendicular segment that connects a vertex of a triangle to the opposite side All right, so as it sits, this definition doesn't take into account this obtuse triangle here. So I have to add this little extra bit in here, or a line containing that side. All right, so just like with median, write something down there for that new segment, that new definition for altitude. Okay, now with this new altitude drawn in here, a different way to prove that the base angles are congruent to each other. It's not like we saw right up here, side, side, side. It wasn't this complicated series of triangles like we saw in the Pons Asinorum. This time we've got our altitude being congruent to itself, of course. We've got a reflexive property there. It's isosceles, so those two sides are congruent. It looks like this is side-side angle again, but it's not, because this is a right triangle, and of course the right triangles have an exception. They're a special case here, which becomes hypotenuse leg. And then again, we're going to get our two base angles are congruent by CP, CTC. And voila, there you go. Again, another rocket bypassing Pons Asinorum, that whole bridge all together. Okay, let's take a look at a couple more exercises here. Whoops. Let's come back over here. And anytime we do these exercises, I do want you to look through the exercise and see if you can work through it on your own. Just pause the video and work through the problem on your own. And then, of course, you can play the video and check to see that you got the right answer. We want to find the value of x. And obviously, we've got ourselves an isosceles triangle, and then one of the base angles is labeled with some algebra. Okay, so again, pause the video, take a stab at it, and let's see what you get. All right, so what we should get here is that all three of these angles, of course, should add up to 180 degrees. And right now, I'm just going to completely ignore this 2x plus 5. Let's just get the angle measurements for all of the angles in the triangle. So I've got 180 that I'm going to subtract 30 from, and I get 150. So these two base angles, which are congruent to each other, have to add up to 150. So if I divide that thing by 2, I'm going to get 75 degrees. Each one of these base angles is 75 and 75, which means, in terms of algebra, 2x plus 5 is equal to 75 degrees. Subtract over our 5. Divide by 2, 35 degrees. Yeah, there we go. All right. Not the only way to do it. You could have done the whole entire thing as one single equation where you have 2x plus 5, plus another 2x plus 5 for this angle down here, plus 30. All of that totals to 180 degrees. You'd still end up in the exact same place. Okay, let's take a look at the next one. All right, this is an SAT question. If AB is equal to BC, maybe I'll mark it here in a minute. Okay, so I have, again, an isosceles triangle. What is y in terms of x? So remember what that means. Again, y in terms of x is that we're going to write ourselves an equation that looks like y equals, and then on the other side it has something involving x. So go ahead and pause, and you try to take a stab at this yourself, play back the video, and see if you got it right. All right, so for this SAT problem, I do want to mark some of this information on the picture. These two segments are congruent to each other, right? It being isosceles, and kind of like the other picture that we just worked with, this angle down here at C also needs to be 3x minus 2, right? Those are the two base angles which are congruent to each other. And now from the previous lesson, we know that this angle right over here, that's an exterior angle. And an exterior angle is equal in measure to its two remote interior angles. And the two remote interior angles are A and C. In other words, 2y should be equal to 3x minus 2. Oh, actually, it's both the same. So I'm just going to write this as 2 times 3x minus 2. I wrote it that way because now what I'm going to do is just divide both sides by 2 and get my final answer as y is equal to 3x minus 2, and be done with it. That's it. We've got y in terms of x. Y is equal to 3x minus 2. Okay, let's see. All right, so that's going to conclude this video. We'll pick it up with the second investigation, looking at the converse of the Base Angles Theorem in the next video.